So what is total amount of heat exchanged with the common reservoir R0? Okay, so the total amount of heat which is exchanged by the n Carnot engines with the common reservoir R0 we'll get them if we add all this term, that is Q10, Q20, then Q30, Qy0 up to Qn0. That is all this term. Okay, so all these terms, okay, these terms, okay, gives us the total amount of heat absorbed from the exchanged with the reservoir R0. Okay, so Q10, Q20, Q30, Q40 like this up to for the nth Carnot engine Q10. If we add all these terms, we will get the total amount of heat exchanged with the reservoir R0. Okay, so the total amount of heat exchanged with the common reservoir R0 is Q10 for the first one, Q20 for the second Carnot engine, Q3 plus Q3 for the third Carnot engine, like this. For the ith Carnot engine we have Qy, 0 plus for the nth Carnot engine we have Qn, 0. So if this is the left hand side, on the right hand side we will have these terms, okay, which this one is coming for the first Carnot engine, this one is coming for the second Carnot engine, then for the third Carnot engine we have this term, then for the ith Carnot engine for this term, then for the nth Carnot engine this term. Okay, so basically we are adding all these terms. Okay, so like this. Okay, so starting from Q10, Q20, then Q30, Qy0, Qn0, then on which is on the left hand side, and on the right hand side we will have this term plus this term, then this term plus this term up to this term. Okay, so this is the left hand side, and on the right hand side we have equal to this right hand side, okay, which is the first term Q1 by T1 T0 plus Q2 by T2 T0, Q3 by T3 T0 plus up to the ith term Qi by Ty T0, then up to nth term. So this is coming from this, the first term, the second term coming for this term, the third term coming from this term, like this. So it implies that on the left hand side we will have, so here you see we can use the summation to generalize this sum. Okay, so we have I equals summation over I equals to 1 to n Q I, 0. So if we put I equals to 1, we will have Q1, 0. If we put I equals to 2, we will have plus Q2, 0. And if we put I equals to 3, we will have Q3, 0. Then for if we put I equals to n, we will have Qn, 0. And on the right hand side, we will have this term. Okay, so which is we can take T0 common from each term. Okay, so we have taken T0 common. Then within bracket we have Q1 by T1 plus Q2 by T2 up to Qn by Tn. Okay, so this summation gives us the total amount of heat exchanged with the common reservoir Q0, which is this one Q0. Okay, equal to, so then again you see we can replace this sum by this summation. Okay, which is I equals to 1 to n Qi by Ti. Okay, so I equals to 1 to n Qi by Ty into T0. So if we put I equals to 1, we will have Q1 by T1 plus for I equals to 2, we will have Q2 by T2. Then for I equals to 3, we will have Q3 by T3, like this. For I equals to n, we will have Qn by Tn. Then this T0. So the total heat exchange from the common reservoir R0 at temperature T0 is Q0 equals to, now T0 is a constant temperature for the reservoir R0, so it will come out of the summation. Okay, T0 summation over I equals to 1 to n Qi by Ty. Now we have already stated that after completion of one complex cycle, the system K return to its original state, right? And no heat is lost or gained by the individual reservoirs, that is individual n reservoirs. Okay, so no heat is lost or gained means next net exchange of heat for this Ri reservoirs, okay, is 0. So hence this amount of heat Q0 which is exchanged from R0 is completely converted to work, okay. Because we have told that while this Carnot engines does operates in a Carnot cycle for once they also does some work. So but all this heat exchange, that is Q1, Q2, Q4, Q6, ultimately after completion of this complex cycle, the net amount of heat gained or lost, okay, for this individual reservoirs is 0. Okay, so we have only these heats exchanged from R0 and some work done performed by this N Carnot engines, or you can say by this whole system K. So for this whole system K, which is comprised of the N Carnot engines, there is only Q0 amount of heat exchanged from the reservoir R0, and it is equal to the work performed by this system K. Okay, because no heat is lost or gained by this individual Ri reservoirs. So the amount of heat Q0, total amount of Q0 which is exchanged from the common reservoir R0 is converted to an equivalent amount of work performed by the system K. So the work performed by the system K after completion of a cyclic process is given by W, which is equals to Q0, which is exchanged from the reservoir R0 at temperature T0, is given by T0 into summation over I equals to 1 to n Qi by T1. So this indicates that complete conversion of heat into work. So Q0 amount of heat is completely converted to work by a system K without any rejection of heat and without any permanent thermodynamic change in this system. Because here you see, we have said that after completion of one complex cycle, the system K returns to its original state and no amount of heat is rejected, okay, or any other kind of exchange of heat, and there is no other thermodynamic change. Its sole effect is the exchange of heat Q0 from a single reservoir, which is R0, and complete conversion of it into work. There is no other permanent thermodynamic change left in this system, and there is no other exchange of heat. This so this implies that complete conversion of heat into work, okay, so which violates the second law of thermodynamics. We know that from this second law of thermodynamics, which is the Kelvin-Planck statement, it states that it is impossible to construct an engine or device which produce no other effect than absorbing heat from a single reservoir and converting completely into work. So this relation implies only that effect, okay, that is Q0 is the amount of heat exchanged from a sole reservoir, okay, that is a single reservoir, and it completely converts it into an equivalent amount of work. But this violates the second law of thermodynamics. So this relation is only possible if it is less or equals to 0. This quantity cannot be positive. If this quantity, if W is positive or Q0 is positive or this term is positive, it will mean that Q0 amount of heat is absorbed and the same amount of heat is completely converted to output work, which violates the second law of thermodynamics, okay. So here this relation is only possible if this is less than 0 or equal to 0. If it is positive quantity, it will mean that the heat is absorbed from a single reservoir is completely converted to work, which violates the second law of thermodynamics. So now what we'll write, that this W equals to Q0 equals to, which is T0 summation over I equals to 1 to n, has to be less than or equal to 0. Okay, so what does it mean equal to 0? So if W equals to Q0 equals to, say, T0 summation over I equals to 1 to n Qi by Ty, if equals to 0, it means that, so it means that no heat is, here now we will use the term, suppose, absorbed, or you can also say that no heat is exchanged from R0 and no work is done. Okay, we have told that W can the work done or this heat Q0, this relation cannot be positive. This term has to be either equals to 0 or negative. So it can be either 0 or negative. So 0 means no heat is exchanged and no work is done, or it is negative, means that Q0 negative means heat is not absorbed from R0. Heat is not absorbed from R0 but is rejected to R0. And W0 negative means work is done on this system K. Okay, so it will mean that if W equals to Q0 equals to this term is equals to 0, there is no heat exchange from R0 and no work is done. Fine, but what does it mean? Okay, so if W is negative, it means that work is done on the system K, composite system K, and then Q0 will also be negative. It means that heat is not absorbed from R0, but heat is rejected to R0. It will mean that W amount of work is done on the system, which is completely converted to heat. Okay, which is correct, because we already know that work can be completely converted to heat, but the reverse is not possible. That is, we cannot we cannot convert some amount of heat to an equivalent amount of work, but the opposite is possible. That is, we can convert some amount of heat energy to equivalent work energy to equivalent amount of heat energy. So W negative means that we do not get any output work, but work is done on this system. Okay, work input is given to the system. Some mechanical energy is supplied to the system K, and that amount of work energy is converted to Q0 amount of heat energy. So W amount of mechanical input work energy is converted to Q0 amount of heat energy, which is now rejected to R0. Okay, which is rejected to R0. Okay, so so Q0, W equals to Q0 is only possible if it is either equals to 0 or less than 0. So sorry, I have not written here Qi by Ti. Okay, so it is only possible if this term is less or equals to 0. Therefore, we have T0 summation over I equals to 1 to n Qi by Ti T0 I equals to 1 to n Qi by Ti less or equals to 0. Okay. Now T0 is constant temperature of the reservoir. Okay, so hence I equals to 1 to n Qi by Ty is less or equals to 0. Okay, so this is the Clausius theorem. Okay, so thus Clausius theorem is proved. Okay, now this equality sign is applicable for the reversible process. Okay, so for the reversible process we have I equals to 1 to n qi by ti equals to 0, whereas the inequality sign is for the irreversible process. So for irreversible process we have summation over I equals to 1 to n qi by ti less than 0.